Okay. Okay, so our lecture tonight um, is on the decoupled Newton-Raphson method. Okay, so last meeting we talked about the load flow analysis. Essentially, we are analyzing a circuit, we are solving a circuit, so we are solving the voltages in the buses in the network. Okay, so once we have solved for the voltages, we can derive the other quantities. Okay, so meaning we can derive the line flows, we can derive the power flows, we can solve for the power injected by the generators, etc., etc. Okay, so as soon as you are able to solve for the voltages, you already solved the network, and you just have to derive the other quantities that we need. Okay, so and then for the Newton, for the load flow, we were able to go through three methods last week, and that was the first one was the Gauss-Seidel solution, wherein we solved the load flow problem as if it's a linear problem. And then I also introduced the Newton-Raphson method, which is a way of solving a system of nonlinear equations. Okay, and for the Newton-Raphson method, we look at the polar form and the rectangular form of the solution. Okay, so take note, guys, that I didn't really went into the full details of the Newton-Raphson method. In fact, we really don't have to really study how it works or the nitty-gritty of the method, because um, there are several software out there that will perform the Newton-Raphson. So I think that there's no use of going through the details, asking you, in fact, to write code on the Newton-Raphson. Okay, if there's already software out there. So the emphasis of this class is how do you use the load flow method as a tool to analyze the circuit, or to analyze the system. In fact, that's what's being required in your load flow assessment. Okay, yun nga lang, I gave you the Gauss-Seidel formulation, but it's not complete. Okay, so there is some coding required from your side, meaning you have to add some lines of code, okay, to be able to solve the problem at hand. Okay, so before we proceed to the decoupled Newton-Raphson, let's have a quick review of the Newton-Raphson method. So this is the Newton-Raphson method. Okay, so essentially, for the Newton-Raphson method, we are solving for the values that we have here. Okay, so the delta of the angles and the delta of the voltages. So take note that initially you have to solve for the bus admittance matrix. Okay, you can get that since you already have all the information on the network, the line impedances, the transformer impedances, etc., etc. Okay, so you can now derive the bus admittance matrix. And then you will initialize all voltages and angles to one angle zero, or you make it equal to the voltage at the slack bus. So if the slack bus is, say, 1.05 angle zero, then you can start at that value, 1.05 angle zero, for all bus voltages. Okay, so all voltage magnitudes will start at 1, and all angles will start at 0. Okay, now and then we're going to use this equation to solve for these numbers here. And once you have solved that, these are the numbers that we will add to the initial guesses for the magnitudes and the angles. So for example, once you have solved for delta V2 and delta V3, you just add that to the initial value, which is 1. Okay, so after the first iteration, you will now have a voltage magnitude of 1 plus delta V2 for bus number 2. Okay, and similarly for bus number 2, the angle will become 0 plus delta 2. Okay, so once you have solved this, you update the initial values by this, and then you proceed to the next iteration. Okay, so now the question is, how does each iteration go? Okay, so so since we're solving for this number, you have to you have to compute for this, you have to compute for that. Okay, so the delta P and the delta Q, essentially using the voltage and the angles, the guesses that we have, you are to solve for the power that's being injected in each bus. And you are to compare that with the known value of P and Q. So essentially the difference, it's telling us how far off are we from the actual value. So since in our first iteration, we initially guessed all voltages to be 1 angle 0, you should expect that when you solve for the P and the Q in in all buses, you will not get the known values. Kasi yun nga, iba yung we're actually solving for the voltages. Eh. So you will get a mismatch. So you are to solve for that mismatch. Okay? And then we will also build the Jacobian. Okay? So for the Jacobian, again, we are getting the partial derivative of P with respect to theta and the partial derivative of Q with respect to theta and also with respect to V. Okay? So we have four types of derivatives here. Either we differentiate P with respect to theta or P with respect to V, or Q with respect to theta or Q with respect to V. Okay? Now, you have to build the Jacobian, and to build that, you just have to look at the parang lookup table na lang tayo. We already have the formulas here. So for the off-diagonal elements, meaning the subscript S is not equal to the subscript R, like this one, Okay, we are differentiating P2 with respect to theta 3, or this one here, P2 with respect to V3. So these are the off-diagonal elements. The subscripts are not equal. So you just have to use this formula. Okay, so you just plug in the values. Okay, so you plug in the value of G, you plug in the value of B. G and B will come from the bus admittance matrix, and then V here are the voltage magnitudes, and then theta S and theta R. These are the angles. Okay, so you just have to plug those in. And that's for the off-diagonal elements. Now, for the diagonal elements, nasaan yung diagonal elements natin? Hindi ko yata nakopya. We have expression for the diagonal elements. It should be here somewhere. Anyway, I missed pasting the diagonal elements, but again, it's another 4 equations that you will apply, okay, to solve for the values here. Okay. So once you solve for the mismatch and once you solve for the Jacobian, you invert the Jacobian, you pre-multiply it to this matrix, and then you will be able to solve for the update values. Okay, and then you keep on doing that until the mismatch is acceptable, meaning the delta P's and the delta Q's that you will get will become smaller and smaller every iteration. Okay, and once it is small enough, okay, you can stop iterating. So how small is small enough? Before you iterate, you decide on a value. It could be 0.001 per unit or 0.0001 per unit. Okay, and as soon as the biggest value here, the biggest among them is less than your tolerance, then you can stop iterating. Okay. Now, take note that in a power system, okay, usually the reactance of the line is much greater than the resistance. Okay, so we model each transmission line as an R, a resistance, in series with a reactance. And usually for a transmission line, the value of X would exceed the value of R. It will be much greater than the R. Okay, so if you get the admittance, okay, if you get the 1 over R plus JX, you will get a G plus JB. And you will find out that the susceptance will be much greater than the conductance. Okay, yung G plus JB na term natin, B will be much greater than G. Okay, so that's parang a reality in the transmission system. Okay, so when you compute for the bus admittance matrix, you will notice that the imaginary components, that the imaginary values will be much larger or usually larger than the real values in the bus admittance matrix. Okay? Now, I think go back to the answers that you got in machine problem 1 and verify that you indeed were able to get those values na yung mga susceptance natin exceeds the conductances. Okay? Now, another observation that we could get from a transmission network is that the angles are very close to each other. So if the slack bus is at angle 0, you will notice that the angles at the other buses will be very close to angle 0. So it could be angle 1 degrees, -1, +2, -2, etc. Okay? So unless you have a very large power system, you will see that the angles will cluster around 0 degrees. Okay? So it is rare that you will get an angle that is very far or that has a that is very far from angle 0. Okay? Perhaps the angles that you will get will be plus or minus 0 degrees. Plus or minus 10 degrees from 0 degrees. Meaning the theta S and the theta R will be very close to each other. Okay, so the angles are very close to each other. So if the angles are very close to each other, it means that the difference, theta S minus theta R, will be very small. And if you get the sine of theta S minus theta R, that will be a very small number, much less than 1. Okay? Now, you may be wondering, why are we interested in this particular term, sine theta S minus theta, sine of theta S minus theta R? Well, that's because if you look at the terms here, meron tayong mga terms na sine theta S minus theta R, sine theta S minus theta R. And if that is very small, then we can make some assumptions like perhaps this term may be ignored and we will just compute for that term. In fact, that is what's going to happen in the next few slides. Okay, we will look at the terms in the Jacobian, and because of this relationship, we will be ignoring some of the terms. Okay. Now, the other consequence of those angles being close to each other is that the theta S minus theta R will be equal to 1, equal to 0. And if you get the cosine of that, the cosine of a small angle is approximately equal to 1. So going back here, you have a cosine theta S minus theta R. So we can now estimate or replace this term here by a 1 instead of using a cosine function. Let's just replace that by a 1 since if we evaluate that, the value is very close to 1. Okay, so take note, guys, that we are making simplifications in our Newton-Raphson method. Okay, we are trying to simplify because if we're going to execute the Newton-Raphson, the full Newton-Raphson method, take note that you have to build the Jacobian, you have to populate this, you have to invert it to get the values here. In fact, we're trying to simplify the computations. Okay, so if you're going to use the full Jacobian, it will involve solving for sines and cosines, etc., etc. And if we have this simplification, then it means that we no longer have to compute for the cosine. Okay, we no longer have to compute for the cosine, and then we can, in fact, ignore this term here because that is very small. Okay, take note, guys, that when you ask a computer to type or to solve for the cosine of a number, a lot of computations are happening inside. Okay, tayo, it's very easy to type cosine of a number. You can use a calculator, it's just a button, cosine of a certain number. But inside of a computer, okay, there is a complex computation that's happening just to get that cosine. In fact, it's using maybe a Maclaurin series or a Taylor series to approximate the value of the cosine to up to a certain decimal point. Okay, so it's not a simple function inside the computer. So we, in fact, are avoiding the use of the cosine and the sine functions. Okay. Now, another consequence of x being much greater than r is that usually the real power flows, real power, okay, yung complex power natin is S is equal to P plus JQ, okay? The real power flows, the P, okay, the P it will only affect the angles, the bus voltage angles, okay? So you see that, notice that if there's a large amount of power from one bus to the next bus, usually you will notice a large difference in the angles, okay, in the voltages on those buses, okay? You will not see any significant difference in the voltage magnitudes, but you will see a significant difference in the angles, okay? And similarly, when a large amount of reactive power is flowing from one bus to the next bus, okay, the flow of reactive power will impact the magnitude of the buses, or the magnitude of the voltage in the buses, okay? So if you see a big difference in voltage magnitudes, okay, you can deduce that the reactive power flowing from one bus to the next bus is significant, okay? So what I'm trying to say here is that the real power flows, it is mostly affected by the angles in the buses, and the reactive power flows are mostly affected by the voltages in the buses, okay? The real power flows will not be affected very much by the voltage magnitudes, and the reactive power flows are not affected by the angles, okay? So it means that since this is not affected by the voltage, then all these derivatives here may be ignored, okay? All of these derivatives here may be ignored. Furthermore, since this is not affected by this, okay? So if you have a function, it is not affected by a variable, then if this does not affect this, then the derivative of the function with respect to this variable is zero, di ba? So if the reactive power flows is not affected by the angles, then it means that all these partial derivatives here are very small, or in fact equal, or we may assume that they are equal to zero. So that is the decoupling of the Newton-Raphson method. Okay, so remember previously that we subdivided the Jacobian into 4 quadrants. So the partial derivative of p with respect to theta, we call it J1. The partial derivative of p with respect to v, we call it J2. And then we call this one J3. And then we call this one J4. Okay? So since the derivatives here and the derivatives here are negligible compared to the derivatives here and the derivatives here, we will just ignore them. Okay? And then the terms that we see here, we will further simplify them using these equalities or using these relationships here. So let us now proceed to the next slide. Okay? So what I'm trying to say is that we will now ignore that. Okay? We will ignore them. Those will become zero. So our big equation will now be broken down into 2 small equations. Okay? And breaking it up is what we call PQ decoupling. Okay? We are just solving for P. We are solving for the angles using the power mismatch. And we are solving for the voltage, the delta V's, using the reactive power mismatch only. So that's the P and Q, PQ decoupling. Okay? Now, let us further simplify by taking advantage of these relationships. That's what's going to happen in this slide. Okay, sige, I'll stop there, okay? So I think the emphasis of this slide lang is the decoupling, okay? So before we further simplify the network, or the equations rather, we're going to look at the alternative formulation of the Newton-Raphson load flow, okay? So we're going to look at the alternative formulation. Take note, guys, here we have delta P's, delta Q's, delta deltas, delta theta, and delta V. Okay? We will just make a few modifications dito. Okay? How are we going to do that? Okay? So, going back to our original expression, this is how we compute for the real power. This is how we compute for the reactive power. Okay, so if you're wondering where this came from, just go back to the previous lecture, we computed for S, that's equal to P plus JQ, and that's equal to S. It's equal to V times I conjugate. Okay, and then we evaluate V times I conjugate, and then we picked out all the real terms. The real terms will be P, and the imaginary terms will be Q. Okay. Now, we can rewrite this expression. It will look like this. And we can rewrite this expression. It will look like that. Okay? You may be wondering, paano naging ganito itong expression na to? Okay? Take note, guys, that this is a summation. J is from 1 to n. Okay? In the summation, we will simply exclude j equal to I. Okay? So take note, this is P sub I, then j is from 1 to n, and then eventually there will be a value, there will be a term here where j is equal to I. So when j is equal to I, you will have a yii, vi, cosine of theta ii plus delta I minus delta I. So you will have a delta I minus delta I, so that will cancel. Okay? So you will have a cosine theta ii. Excuse na. Chin. Okay? So you will have a cosine theta ii. And then you have here a vi times a vi. So when you have a vi times a vi, that is your vi squared here. Okay? And then if you have a yij cosine theta ij, that is your gii. Okay? Take note that y is equal to g plus jb. Okay? So y is equal to g plus jb. Okay? So if you multiply the magnitude by cosine theta ij, then that's just g. Similarly, you can do the same for q. Okay? So dun sa summation natin, you just take away the term where j is equal to I, and you are left with this summation here, and then this is the term where I is equal to j. Okay? Now, we can also simplify this equation, or in more compact form, that equation is this one. Okay? So essentially, this part here is the partial derivatives of the p's with respect to theta. Nagkaroon lang tayo ng change in variable. Instead of theta, we're now using delta. So the partial derivative of p with respect to the angles. And then this is J2, partial derivative of p with respect to the voltages. That's the 2 by 2 submatrix here. And then this submatrix here will be J3, and that submatrix there will be J4. So that's J3 and that's J4. Okay? And this is our delta angle, and that's our delta voltage. Okay? Now, we will just make a few modifications in that equation. Let's copy that on the next slide. Okay? So, kinopya ko ba? Hindi ko kinopya. Okay? But what I did here is that you have a delta V there. What if we divide that by V? Okay? We divide that by V. And then we multiply J2 by V, and then we multiply J4 by V as well. So kumbaga, lalagyan natin ng V dito, tapos lalagyan natin ng over V dito, such that when you multiply this with the second column, the V that you have here and the V that you have here will be canceled by the over V that you have there. This is what I'm talking about. Okay? So instead of having delta V only, you will have an over V, but you will have an additional V here and an additional V here. So if you multiply these two matrices together, it's the same as this one. Pareho lang yan. Okay? Kasi nagka-cancel yung V. Okay? This V here will be canceled by that over V. Okay? Now, why are we doing that? Well, that's because it will further simplify the expressions. Okay? Now, we will now rename, this will be our new J1, this is our new J2, this is our new J3, and that's our new J4. Okay? So, using using the terms for J1, this is what we will get. Okay? And then, and this is for the off-diagonal terms. For the off-diagonal terms, ito yung makukuha natin. Okay? Now for J3, J1, J3, J3 is this one. Okay? So for the off-diagonal terms, this is what we will get. Okay? And then for the diagonal terms, this is what we will get. Okay? By the way, you can verify that these are the expressions by differentiating this. You get the derivative of these expressions. We're no longer getting that. It's already done for you. Okay? Either you get that term, or you get that term, or you get this term, or you get that term. Okay? And then for J2, you will either get that, no, not that one. You will either get this term here, or you will get that term. So you will have that term for the diagonal elements, and then, the off diagonals, and then for the diagonal elements, this is what you'll get. Okay? And then lastly, for J4, you will either get this term here or that term. Okay? And this term, you will use that for the off diagonal terms. Okay, the subscripts are not equal. And then for the diagonal terms, you will have that term. Okay? So this is now our new formulation for the Newton-Raphson method. Okay? So you will now have this. Okay? Any questions, guys? Okay? So ang ginawa lang natin, yung previous formulation natin last meeting, wala tayong over V dito, wala tayong V dito. Ngayon, nilagyan lang natin ng over V doon at ng V dito, and we are getting new expressions. Okay? Now, wait lang ha. Wait lang, guys. Can you please go out? I'm having a lecture. Thank you. Okay. Sige. So, at this point, what we're going to do is we're going to use this alternative formulation of the Newton-Raphson load flow for the decoupling. Okay? Siya na yung i-decouple natin. So, it means that since we have established that delta P will not be affected by delta V, and that delta Q is not affected, or is not dependent on delta delta, we will make this 0 and we will make that 0. Okay, and that's our decoupling. Ito na siya. So we are now decoupling. Okay, so we are setting J2 to be equal to 0 and J3 to be equal to 0. Okay, we will call J1 as H and J4 as L. Okay, so we are now left with two smaller equations. That is, delta P is equal to J1 times delta delta, which is that one. And then delta Q is equal to J4 times delta V. And if we are using our alternative formulation, so using the alternative formulation, the first equation is still the same. That is, delta P is still equal to J1 times delta delta. But since we are now using the alternative formulation, yung may V doon and then an over V here, this is what we'll get. Delta Q is equal to J4, that's our new J4, okay, times delta V over V. Okay? Sundan ba, guys? Okay. Now, so we are now left with two formulations, okay, two smaller equations. And then moving on, so we have J1. Okay, so I'm just copying the expressions that we have here. So this is J1, that is J4. We are ignoring this. We are also ignoring that. Okay, so let's copy the expression for J1. We have that. Either we have this term or we have this term. Take note, we are using this term for off-diagonal elements, and we are using this expression for diagonal elements. For J4, ganun din. For the diagonal elements, for the off-diagonal elements, we are using that expression. And then for the diagonal elements, we are using this expression. Take note, guys, that if you inspect, these terms here is just the same as that one. Parehong-pareho lang. We have VI, VJ, YIJ, sine theta ij plus delta J minus delta I. Pareho lang nito. So you have Vj, Vi, Yij sine theta ij plus delta j minus delta I. The only difference between the off diagonals here and the off diagonals here is the negative sign. Okay? Sorry. No, there are no negative signs. They are actually the same. Okay? So partial of P with respect to delta is equal to V times partial of Q with respect to V. Okay? So the terms are the same. In fact, that is the advantage of using that formulation. Okay, you may be asking, bakit pa natin pinahirapan yung sarili natin, ano? Na nag-multiply ng V doon at nag-divide ng V. Well, the main advantage of doing that is that once you have solved for the values in J1, the off-diagonal elements, you already have the values in J4. Okay? You are hitting two birds with one stone because of that modification. Okay? Now, how about submatrix J1? Okay, you have a Q. You already know that. Yeah, you can compute that. Okay, and then we have a V, and then we have a BII. Okay, so ito, whatever you have there, marireuse natin doon, and then whatever you have here, marireuse din natin dito. So the equations, we will be able to simplify the equations. Okay. Now, so take note here that meron tayong mga sign terms there. We will further simplify them. Take note that if the differences delta I minus delta j are very small, then we can approximate cosine theta I minus theta j to be 1, and sine of theta I minus theta j, delta I minus delta j to be delta I minus delta j. Okay? The sine of a small angle is equal to the angle. Okay? Ito na nakita na rin natin to. B is greater than G. Okay? So if you're going to look at the previous expression, okay? May mga matatanggal tayong terms dyan. And then Q sub I is much less than VI squared BII. Okay? So the reactive power injected into a bus will be much less than the reactive power if all lines from that bus were short-circuited. Okay, take note that BII, that's the summation of all reactances connected to bus I. Okay, and this will be equal to the reactive power that will flow through all those lines if the other ends of those lines are shorted to zero. And that term will be much larger than this term here. In fact, the main benefit of having that assumption is that if you look at this expression, we will ignore that term. We will ignore that term, and we will also ignore this term here. Okay, guys? Okay? Now, moving on. Okay? So since this term is much greater than that term, then this term here will overwhelm that term in J1. Hence, for the diagonal elements, we will just approximate partial of Pi with respect to delta I as negative Vi squared Bii. Okay? And then for the off-diagonal elements, we will ignore this because delta I minus delta j is negligible. That is theta ij minus delta I plus delta j is just theta ij. We are ignoring that difference. And then sine of theta ij, when you multiply that by or to yij, it's just equal to bij. Okay? And then you will still have the other two voltage terms, negative Vi and Vj. Okay? And we will do the same for J4. So for J4, remember we originally have that term. Since this is much greater than that term, we will just ignore that term. That is, this term here, yung diagonal element kay J4 will just become like that. Negative Vi squared Bii. We are now ignoring that. And then for the off-diagonal terms, we have that expression, or we have this expression here. Okay? We have that expression there. But we are ignoring these terms here, the deltas. So you have a yij sine theta ij. Those two put together is just bij. Okay? Now, how will the expressions look like? So for the first equation, you have delta P equal to J1. Again, that's J1 times delta Ij. All terms will just be negative Vi, Vj, Bij times delta of delta J. Kumbaga, lahat ng terms dito, whether diagonal term or off-diagonal term, will just look like that. Okay? So if you're not convinced, let's go back to the previous slide. Kay J1, ayan. So either you have that term, Vi, Vi, Bii, or Vi, Vj, Bij. The term is just equal to this, whether I is equal to J or not. That is, J includes I. So if I is equal to J, then you just have a negative Vi times Vj, Bii. Okay? So if they're not equal, then you have that term. Similarly, for J4, you either have that or you have this. Okay? So parehang-pareho lang. Negative Vi, Vj, Bij. And if I is equal to J, you have this. Negative Vi times Vi times Bii. Okay? So this is what you will get. Okay? And these two approximations will lead to the following equations. Okay? So, ang gagawin lang natin is, looking at the first term here, we will factor out the first V's. Itong mga first V's na to, no? So, yung lahat ng Vi, lagay natin dito. And then, all V sub J's, andun. And then, meron tayong mga constant term, Bij. Ito naman sila. Okay? Similarly, for the second equation here, we factor out all Vj's, ito sila. And then all Bij, ito sila. And then all Vj's, ito sila. Okay? And then on the right side of equation, you have a delta delta and a delta V over V. Okay? So this is a very simplified version of our Newton-Raphson load flow. Recall that in our full Newton-Raphson, you have to solve for the Jacobian in each iteration. But here, you no longer have to solve for the Jacobian in each iteration because this matrix here, it's just a constant. These are just constants. These numbers can be derived from the bus admittance matrix, which you already know. Okay? So take note, guys, that in the full Newton-Raphson, you have to invert the Jacobian in each iteration. Here, since this matrix is fixed, you just have to invert it once. And that's it. Okay, you just have to invert it once. Or if you want to get the LU factors of that, you just have to get the LU factors once. And that's it. Okay? That's it. Okay? So you no longer have to solve for a Jacobian every iteration, and then you don't have to invert a matrix every iteration. You have these two equations here. Okay? Now, we will just rewrite this equation as delta P, that one, times a voltage matrix. Take note that that voltage matrix, diagonals lang yung laman niya. This is the voltage at bus 1. Magnitude lang to, voltage magnitude at bus 1, bus 2, up to bus n. This is just a constant, and we will call that as the B prime matrix. And then this is another voltage matrix, voltage magnitude at bus 1, bus 2, bus 3, etc., up to bus n. That's our bus magnitude matrix here. And this delta delta here is just that matrix. This matrix, we will call that B prime. Okay? And then for the second equation, you have delta Q equal to the voltage magnitude matrix multiplied by a B matrix, which is B prime prime here, And then another voltage magnitude matrix here. Again, diagonal elements lang sila lahat. Like that. Like this. Siya lang yun. Multiplied by a delta V over V matrix. And that matrix is this one. Okay? Questions? Any questions? Okay. Now, another another thing that we have to take note of is that all the terms here is negative b. B11, negative B12. We are dropping the negative sign here. Okay, we are dropping the negative sign. We are also dropping the negative sign here. Okay, but we will define B prime and B prime prime as the negative of the imaginary part of the bus admittance matrix. Okay, so again, from the Y bus, you just get the imaginary part of the Y bus, and then you get the negative of that. Okay? One more thing to take note of is that B prime is of order n minus 1, meaning its dimension is n minus 1 minus n, n minus 1 by n minus 1. Take note that for B prime, so this is B prime, we are solving for the angles. And take note that we are solving for the angles in all buses except for the slack bus. So if there are n buses, then we are solving for n minus 1 angles. We are solving for n minus 1 delta deltas here. Okay? But for B prime prime, its order or its size, its dimension is n minus 1 minus m, where m is the number of n is the total number of buses and m is the total number of PV buses. Take note that in the PV buses, we already know the voltage. So we are not solving for the voltage there. In fact, we are just solving for the voltages in the PQ buses. And how many PQ buses do we have? Well, it's equal to the total number of buses, n, minus the slack bus, 1. We only have one slack bus, minus the number of PV buses. So this number here, n minus 1 minus m, that's the total number of PQ buses. Okay? So at this point, we are now ready to solve for the fast decoupled load flow. Okay? However, there is still one more simplification. And that is by considering that the voltage magnitudes are all equal to 1. Take note, guys, that when we solve for the voltage, we are expecting that all of them should be close to 1 per unit. Diba? In the transmission network, the voltages there is 1 per unit plus or minus 0.05. It should be, the voltage in the transmission network should be 5% within the nominal value. Okay? So since the voltages are all very close to 1, we are further making a simplification for this matrix. We will just assume that all the values here are 1, effectively reducing that network or that matrix into an identity matrix. Okay? Ito, we're solving for the V, so we're not making the voltages here 1. But here, we are making all the voltages equal to 1 as a simplification. Okay? So if the diagonal elements here are 1, then this is just reduced to an identity matrix. Hence, we are now dropping that matrix in this equation. So we will replace this by an identity matrix, or we don't even have to write the identity matrix there. We will also do the same here in this matrix. So we have a square matrix, all the diagonal elements is equal to 1. So this will be replaced by an identity matrix, so we will just drop it. So this equation will just evolve to delta P equal to the voltage magnitude matrix, like so, times B prime times delta delta. Mawawala na siya, this one here, or that one. Okay? We no longer have the V matrix. Okay? So, baliktad yata yung ginawa ko. I dropped this one, pero yung ginawa niya, he dropped the one on the left. Anyway, this is just a constant. That's a constant, so it doesn't really matter that much. Okay? So we have B prime times V times delta delta. Okay? And then we have a B double prime times V times delta V over V. Okay? Any questions at this point? Okay. Now, so if there are no questions, let's just proceed. Take note, guys, that when you're now solving the Newton-Raphson using this formulation, there are two versions. You have the BX version or the XB version. So the XB version, which is called the Stott and Alsack method, okay? Ang sabi kanina, no, the B matrices are just the negative of the imaginary part of the bus admittance matrix. However, when we solve for the B prime and the B double prime, there is a version wherein the resistances are ignored. So in the XB version, we will ignore the resistance in the calculation of the B prime. But we will include the resistance when we compute for the B prime prime. Okay? Now, you compare that with the BX version. For the BX version, that's the von Amerogen version, okay? We are ignoring the resistance in the computation of the B prime prime, but we are including the resistance in the computation of the B prime. Okay? So yun lang yung main difference ng dalawa. Okay? So, in the XB version, the elements of the B prime matrix is computed like so. By the way, you may be wondering, saan ang galing tong mga to? Again, take note that in the Y bus, oops, what just happened? Okay, in the Y bus, okay, in the Y bus, the elements of the Y bus, I think I'll just have to put some text here, The elements of the Y bus, you have a Y, Y ij is equal to Gij plus J Bij. Okay? So this is the real component. That's the imaginary component. Okay? So itong mga B na to, sila na yon. You just get them, you just copy them from the bus admittance matrix. Okay? So you just plug them in. So you plug in here, okay? And then you get the summation, you get the negative, and that's B prime prime. Okay. Similarly, B prime rather. Similarly, when you compute for the B prime prime, you use these terms. And again, where did this come from? From the bus admittance matrix. Okay. Now, take note, guys, that in the computation of the B prime prime, take note the B prime prime is for the computation of the reactive power flow. You have to include all the shunt reactances to ground. So if there's a reactance from the bus to neutral, you have to include that in the B prime prime computation. However, when those reactances, they do not affect real power flow. So you do not include them in the B prime computation. You only include the reactances from bus to neutral in the B prime prime computation. Okay? Sige. Mamaya, meron tayong mabilis na example. Okay? That's why medyo nagmamadali rin ako ng konti. So, because I want to get to the example. I think that's the best way to demonstrate the BX version and the XB version. Okay? Now, that's the XB version. For the BX version, babalik na rin lang natin yung terms. Okay? So for the BX version, we will use this expression for the B primes, but the B prime primes, yun yung direct copy. Direct copy lang siya. And take note, for the B prime prime, we have to include the shunt reactances, the reactances from the buses to neutral. Okay, so that's the BX version. Okay? Sige. So I think at this point, we just have to have a quick summary and then let's go to an example very quickly. Okay. So if we're going to use the fast decoupled load flow, this is the solution steps. Okay. First, we have to assemble the B prime and the B prime prime matrices.
It's 7
okay.
o'clock.
Whether we are using the XB version or the BX version. Okay. If you're using the XB version, you just have to assemble the B prime and the B prime prime matrices that way. Okay. If you're using the BX version, then you assemble the B prime matrix that way and the B prime prime matrix that way. Okay. So assemble the B prime and the B prime prime matrix, get the LU factors. Again, we're simply inverting B prime and B prime prime. Okay. And then we compute the power mismatch, delta P. Okay. And then we divide the delta P by V. Okay. And then we are now solving for delta delta using this equation. By the way, guys, where did this come from? Ano? Bakit may nagkaroon ng V kaagad sa ilalim? It's just this equation here. Okay? It's this equation here. Okay? That one. Okay? It's that equation. Okay? Naglagay lang tayo ng V sa ilalim. Okay? And then, we will be able to get the angles. Take note, guys, that when you solve that, the angles that you will get will be in regions. So you have to be careful. It is not in degrees. It will be in regions. So you have to convert that to degrees, or you use the regions muna. Okay? And then later on na lang, once you have the answer, you convert everything to degrees. Okay? And then you check for convergence, meaning compute for the delta P's again and the delta Q's, and then you compare that to the tolerance. If there's at least one element that is greater than the tolerance that you've set, proceed with the iteration. Okay? And then you go to the next half of the iteration. That is, you compute for delta Q over delta Q over V, and then using B prime prime, you solve for delta V, and then you update the magnitudes, the voltage magnitudes, and then you check for convergence again. Okay? And then you keep on doing that until you reach convergence. Okay? So by the end of the meeting, by the end of this evening, I will be giving you the second machine problem. Okay? And that machine problem is due at the end of the year, December pa. Okay? You'll have around 5 or 6 weeks to do that. Okay? And you will either you will be writing. You're going to write a script, an octave script, for the fast decoupled load flow. Okay, for the fast decoupled load flow, meaning you're going to implement this. You're going to write an octave script that will implement this, and you will either implement the BX version or the XB version. Okay. Pero kung sino yung mag-implement ng BX and XB version, mamaya natin malalaman. Okay, before we go. Okay, so hindi ko muna sasabihin ngayon, okay? Para lahat tayo nakikinig dun sa BX version and the XB version. Okay? Now, let's have the guys that will be doing the BX version is quite lucky, because there's an example. Okay? So in this power system, quick lang, sagutin natin to. Okay. We will compute just one iteration for this power system. Okay. So it's a 3-bus system. We have here a slack bus. This is bus 1 is our slack bus. It's 1.05 angle 0. Bus 2 is a PQ bus drawing 400 megawatts and 250 mVars. And bus 3 is a PQ bus, a PV bus rather. PV bus, where that generator is maintaining the voltage there at 1.04 per unit, and that generator is injecting 200 megawatts. We already have the bus impedances here, the line impedances rather. So these are the line impedances, and when you compute for the bus admittance matrix, this is what you'll get. Okay, hindi na natin i-compute yung Y bus. Okay, I trust that using these impedances here, you will be able to compute the Y bus. Okay, so the next step is we will compute for the B prime matrix. Okay, we will now solve for the bus voltages using the fast decoupled load flow and the BX version. So when we use the BX version, it means that we will be computing for the B prime and the B double prime matrices using these expressions here. Okay? So let's now proceed to the example. Okay? Take note, guys, that In this network, we already know the voltage and the magnitude here. It's 1.05 angle 0. Here, we already know the magnitude. So we are just solving for the voltage magnitude here. Okay? And furthermore, we are only solving for the angles here and here. The angle here is angle 0. Okay? So it means that we are only solving for V2, hence we are only solving for delta V2. Okay? We are only solving for the angle at bus 2 and the angle at bus 3, hence we are only solving for delta at bus 2 and the delta at bus 3. Okay? So these are the two decoupled equations that we are solving. Okay? These are the two decoupled equations that we are solving. Take note that we are also getting the values of the B prime and the B prime prime matrices from the Y bus. Okay? So going back to the definition of the B prime and the B prime prime, B prime and B prime prime are just the negative of the imaginary part of the bus admittance matrix. Negative, the imaginary part. So ang gagawin lang natin dito is that we will lift the values of the bus admittance matrix and then we will get the imaginary part. We will get the negative. Okay? So G12 plus JB12 is just equal to the negative of Y12. Ito yung Y12 natin. Sorry. This thing here, that's Y12. And the negative of that is 10 minus J20. Okay? How about the negative of Y13? So this is Y13. The negative of that is 10 minus J30. The negative of Y23 is just the negative of that term, or 16 minus J32. Okay? So at this point, let us now assemble the B prime matrix. Okay? So for the B prime matrix, okay, I think kailangan kong magsulat, ano? Okay? I'll just, oops, dapat dito yata ako. Okay? Pasensya na kayo, wala akong pen, ano? So I'll just use the text. Okay? So what we want to solve for is B22, B23, B32, and B33. You may wonder, bakit wala tayong row 1 and column 1? Take note that bus 1 is the swing bus. We are not solving for the angle at the swing bus. Hence, in the B prime matrix, bus 1 is not included. Okay? All buses where the angles are already known, that's only the slack bus. Okay? Those buses are not included. So we are including all buses in B prime except the swing bus. So we do not have a row for bus 1. We also do not have a row for a column for bus 1. So this is B22, B23, B32, and then B33. Okay? Now, how do we get the value of B23? Okay? So B23, we're going to use this term, B23 prime. Lagyan natin ng prime rather. Okay? I hope naintindihan nyo what I'm trying to write here, no? B23 prime. I'm using the underscore just to indicate that the 23 is a subscript. Okay? It's equal to B23 squared. Yan. Challenging pala to. Squared. Yan. Plus G23 squared. Okay? And then that will be over, and then over that, you have B23. Nasundan ba, guys? The equation. I'm trying to write this equation here. Okay? Okay? So you have B23 squared plus G23 squared all over B23. Okay? And how do we get the values? Ito yung this is a B23. B23 is equal to negative 32 and G23 is equal to 16. Okay? So B23 is negative 32 squared plus 16 squared. Okay? So that's B plus G. Just we're looking at this, huh? By the way, yeah, may negative sign doon. And then you divide that by negative. You divide that by negative 32. That's your B23 there, which is this one. Okay? So if you solve for that, that is the negative 40. So if you have your calculators there with you, that negative 40 is this thing here. That's the B prime 23. Okay? Now, how do we get B prime 22? Okay? So B prime 22, we will now use that expression. It's equal to the negative of B prime 12 plus B prime 23. Okay? The summation I excludes J. So, hindi kasama yung B22. Siya nga yung sinusolve natin. Okay? Now, we already know the value for B prime 23. Okay? So, B prime 23 here, okay? Itong value na to, that's your negative 40. So, we still have to solve for B prime 12. Now, how do we get B prime 12? We will also apply that expression. Okay? So, B prime 12, okay, it's equal to B12 squared. So B12 is negative 20. I hope you can follow me, guys. Squared. Okay. So ito yun. This one, negative 20 plus yung 10. That's the G. That's the G12. Okay. I'm writing G12 and that's 10 squared. Okay. And that will be divided by B12. And B12 is negative 20. So that's negative 20. Okay? So if you have your calculators with you, okay, the numbers that we will get there is negative 25. Okay? So going back to B prime 22, that is equal to the negative of negative 25, which is this thing here, B prime 12, plus negative 40. And that's your 65 over there. Nasundan ba, guys? Okay? Very quickly, let's do the second row. Let's do the second row. Itabi muna natin to sa taas. Okay? Let's do the second row. Okay? I hope you're copying with me. So we're now on the third row. So this is B13. So that's B13. Okay? B prime 13. And B prime 13, we will now use this expression. It's equal to B13 squared, okay, plus G13 squared divided by B13. Okay? Kopyahin natin yung mga values. Ang tinitingnan na lang natin ngayon ito. Si G13 and B13. Yung mga yan. Ayan. So, yung 10 minus J13. Okay? So, you have here B13 squared. So, that's negative 30 squared plus 10 squared. That's your G13. Ito yung G13 natin. Okay? And you divide that by negative 30. Okay? So that's negative 30 squared plus 10 squared. And that's, I think that's negative 33.33. Okay, that's 1,000 divided by negative 30. Okay? Now we also have to solve for Since this is equal to that sum, okay, kailangan natin gamitin si B23, which is ito, yung negative 40 doon. Okay? So B prime of 33 is equal to the negative of B prime 13 plus B prime 23, okay? And that is equal to the negative of negative 33.33, which is this thing here, plus yung B prime 23, negative 40. Negative 40. Hence, you have a negative 73.33, which is that thing there. Okay, folks? So that's our B prime. Okay? So again, ina-apply lang natin itong expressions na to. Okay? Now, how about B double prime? How about B double prime? Okay? So for B double prime, we will just apply this. Okay? So take note that for B double prime, we're just writing the B double prime matrix for the row or for the bus where we are solving for the voltage. And going back to the network, we are only solving for the voltage magnitude at bus 2. We already know the magnitude here and the magnitude there. Hence, we are not writing B prime prime for buses 1 and 3. We are only constructing B prime prime for bus 2. Hence, yung B prime prime natin is a 1-by-1 matrix. In fact, ang laman niya, 52 lang. Now, you may wonder, where did that 52 came from? Okay, that's what we will do next. Okay, so I'll just put this thing aside muna. Put this thing aside because I'm going to use the space. Okay. How about B prime prime? So I am solving for B prime prime underscore 22. And from this expression, it's just equal to it's just equal to B 22. Okay? Nasundan ba? Oh, sorry. No. I should be using this, the summation here. Okay? I'm using that summation. However, we do not have a reactance from bus to neutral. So at bus 2, we do not have a reactance connecting that bus to neutral. It means that this term here is equal to 0. So this thing here is equal to the negative of B prime prime 1, 2 plus B prime prime 2, 3. So it means that we have to solve for B prime prime 1, 2 and B prime prime 2, 3. Fortunately for us, B prime prime 1, 2 and B prime prime 2, 3, ito lang. We will just have to copy. Okay? And that is just equal to negative of B 1, 2 plus B 2, 3. Okay? Ito lang siya. Okay? Now, what is B 1, 2? B 1, 2 here is negative 20. And then B 2, 3 is this thing here, negative 32. And that's equal to the negative of negative 52 or 52. So that's how we construct the B prime prime matrix. Okay? So now that we already have the B prime and the B prime prime matrix, what's next? We will now execute the fast decoupled load flow. Okay, it's what's happening on the next 2 slides. So let's do that. Okay. So first, you have to solve for P. So you initialize. We initialize V2 to 1 angle 0. We initialize the voltage here to 1 angle 0. And we initialize the angle here to angle 0. Okay? Now, using all those voltage magnitudes, say V1, 1.05 angle 0, V3, you have 1.04 angle 0, and V2, 1 angle 0, we will now solve for P2, P3, and Q2. Okay? And then we will compare P2, P3, and Q2 to the scheduled power. So take note that for bus number 2, we have a power injection of negative 400 megawatts and negative 250 mVars. And using 100 MVA as the bus voltage, as the base power, the scheduled power is negative 4 minus J2.5. So that's the 400 megawatts, and that's the 250 mVar divided by 100. So negative 4 minus J2.5. Okay. Now for bus number 3, the scheduled injected power, this is injecting 200 megawatts. Hence, the scheduled is 2 per unit. Okay. Now, at this point, we will now solve for the power at bus 2 using all the values here. So we will just plug it in sa equation na to. Now, you may be wondering, sir, saan nanggaling yung equation na yan? I saw that somewhere up here. Ang taas niya. Here. We will just apply that equation. Okay? So you already know the G's and the V's and the Y's. And then the V's here, ito yung mga either the node values or the guesses. And then these deltas are the angle zeros. Okay? So we are simply evaluating that expression. And for the three buses, we have this. Either this is P2, that's for P3, and that's for Q3. And so for P2, once you have evaluated that, you will get negative 1.14. For P3, once you have evaluated that, you will get 0.5616. Now for bus 2, the scheduled power is negative 4. However, using these bus voltages, the computed power is negative 1.14. So we are off by negative 2.86. Similarly, for P3, the scheduled power is 2, but the computed power using that line is 0.5616. So we are off by 1.43. Okay? So we are now writing this equation. So delta P2 over V2 is negative 2.86 over 1 because our guess for V2 is 1. And then delta P3 over V3, ito yung delta P3 natin over V3. And V3 is 1.04. Okay? This is B prime. We are now inverting it. We now multiply that to our delta P over V matrix. And this is what we will get. And take note, folks, that this is in regions. These are in regions. So after the first half iteration, delta 2 is 0 plus that, or negative 0.048761 regions. And delta 3 is 0 plus that angle, or negative 0.007737 regions. Okay? Now, the next step is to evaluate Q2. What is the reactive power here? Oops, here. And then we will compare the computed reactive power to 250 mVars. Okay? So, we will now use these values for the angle. So that's why nakikita nyo, no? Ang ginagamit na angle, ito na. Okay? Yung ginagamit na angle, yun na. Okay? Now, where did that came from? That 2.03, that came from the Y bus. Okay? That's the angle of the particular values of the Y. Okay? So we will just use that expression, plug in the values, and the injected reactive power is negative 1.0354, and we are to compare that with the negative 2.5. And at ang sabi niya is we are off by negative 1.4646. Okay? Now, we will solve for the delta V2 here. So it's equal to delta Q2 over V2 multiplied by the inverse of B prime prime. So yung B prime prime natin is just 52. Hence, we get this. 1 over 52 multiplied by delta Q, that's delta Q, over V2. And the delta V2 is negative 0.028165. And that is what we will add to V2. So this is our initial guess. Subtract, or you have to add this. So this is the value of V2 for the next iteration. And then you have to do it all over again. Okay, guys? Questions? Questions, folks? Wala na? Okay. Sige. So that's now the that is now the BX version. Now, what are you going to do, or how will this become different if you're going to use the XB version? Well, for the XB version, the main difference lang is that for the XB version, ito naman yung gagamitin nating equations to compute for B prime and B prime prime. Recall that for the BX version, ito yung ginagamit natin to compute for B prime. Ito yung ginagamit natin to compute for B prime. This one is for B prime prime, this is for B prime. For the BX version. For the XB version, baliktad naman sila. Okay, so compare, compare. So this is the expression for B prime for the XB version. For the BX version, andito na siya sa baba. Okay? And then for the BX version, we have this to compute for the B prime. However, those are the expressions that we use to compute for the B prime prime. So baliktad lang sila. Okay? So at this point, let us now proceed to the overtime na tayo. Sige, try natin matapos in a few minutes, 7:30. Okay. So at this point, I will now give you the machine problem. So the machine problem is already at the UVLE. Okay, it's already at the UVLE. It's here, kaya lang it's still hidden. Anyway, I'll make it available na for everyone. So I'll just make it available to you. Bakit ayaw mag-turn on ng editing? I'll just make it available for you. So later on, pag tingnan niyo yung UVLE, you will now, I'll just